In this video, I'll be introducing different sizes of infinity. So, first off, what is infinity? Well, you might say infinity is like the number of natural numbers, right? All of 1, 2, 3, 4, all the counting numbers, right? That's infinity. Right there. Infinity is the number right there. But that's a kind of skewed way to look at it, right? Because, well, what about the real numbers, right? Like all the decimals. All the decimals. Like 3.14159 and 1.6164 and 2.781828, right? All these are in the real numbers, right? And you can continue that on infinitely. Is that same infinity? Well, how do I know that these two are the same size, right? How do I know that the natural numbers, which is usually, the natural numbers is equal to the real numbers? How do I know that? Now, how do I know that the sizes, they're not equal to each other? The sizes of them, you usually put absolute value signs. Okay? How do I know those are equal or that they aren't equal? Well, let's take a look at finite sets, right? Like the set of 1, 2, 3, right? That has 3 elements. 3 elements. Well, so does the set ABC. 3 elements. How do I know that they have the same size? Well, what you can do is you can pair each one up. 1, I'm going to put over there. So A is paired up with 1. Okay, now I can't use A or 1 again. Can't use them again. Now off with these two. Okay, so A and 1 are gone. Okay, I'm going to match up 2 with B. 2 with B. Right? Now I can't use those again. Okay, of course I'm going to match up 3 with C. Now I can't use those again. And look at that. We've eliminated all of them. That's what happened. We just created a map, a mapping, ABC, a mapping that brought 1 to A, 2 to B, and 3 to C. What did we do? Well, we made sure that we couldn't use any of these twice, and we made sure that we couldn't use any of these twice. And we made sure that everyone in the output is hit by something in the input, right? That's how we made sure. If I instead added a 4th element, D, no mapping would exist because I'd have to make another path right there. But you can't do that because then it wouldn't have a property, right? Because then you'd be left with nothing on the top, but you still have D on the bottom. So they're different sizes. So what did we do? We created a map F that brought you from one set into the other set, such that, this is what that means. It takes in an element of this set, and it outputs an element of this set, usually denoted F of A. Looks like F times A, but it's F of A. Okay, such that. Okay, what do we need? Well, we need that if two elements are equal to each other, that their functions evaluated them is equal to each other. Okay? So meaning that one cannot go to two values. Okay? One cannot go to two values. Any element cannot go to two values. And we also need to make sure that if their function values are equal, then they are equal. Right? Because if I look at this map again, and I instead had the set of A and B, right? You know these don't have the same size. And I map 2 and 1 to the same thing. Well, guess what? F of 1 is A, F of 2 is A. They are equal, but X is not equal to Y. And that's why this doesn't work. And we need one more property, that any B that I choose from B, okay, any element in B, okay, so in our example 1, 2, 3, into A, B, C, I can choose there. I can choose any one of these. I can choose A, B, or C, and there's something that maps to it. Any B, an element of B, there exists an element of A, such that F maps to B. Basically meaning everything in the output is hit. Okay, everything in the output is hit, and you can't send two different elements to the same element. This is what is called a bijection. F is called bijective. Okay, now this is a little kind of abstract. If you don't understand it, just think back to this. Okay? This example, right? If I send 1 to A, 2 to B, and 3 to C, right? No two elements go to the same element, and every element in the output is hit by something in the input. That's what a bijection is. Okay, what does this have to do with different sizes of infinity? Well, it gives you whether the real numbers and the natural numbers are the same size. So, what does it mean for something to be the same size as the natural numbers? Okay, so I have my set of natural numbers, 1, 2, 3, on, and I want to see if this is, say, equal to the same size as the set of integers, 0, 1, -1, 2, -2, so on. Right? I say it is. Why? Because I can create a bijection. 1 goes to 0, 2 goes to 1, 3 goes to -1, I'll write out more terms, 4 goes to 2, 5 goes to -2, and so on. How is this a bijection? Well, each one goes to a unique one of these, and every one in this is mapped to by one of these. Right? So this mapping is bijective, therefore they're the same sizes. Now, there's a different way to look at this, namely, that if I list them out in the standard way, right? List them out in the standard way, I can list them. 1, 2, 3, 4, 5, right? That's just the bijection written in a different way. Maybe write it like that. Right? So we just list them out. That's it. So can we do that with the rational numbers? The set of all fractions? Right? Well, I'm going to list out the rational numbers, and I'm going to show you that they are the same size as the integers. Because if I have 1 over 1, right? So over here I'm going to have 1 over 1, then I'm going to have 1 over 2, then 1 over 3, and so on. then I'm going to have 2 over 1, 2 over 2, 2 over 3, so on, 3 over 1, 3 over 2, 3 over 3, and so on. You can imagine continuing that out in all directions, right? Now you can see I'm overcounting because 2 over 2 is the same as 1 over 1, and 3 over 3 is the same as 1 over 1. And then down the line you're going to get 6 over 3, which is the same as that, but we're overcounting, so it's fine. If we're overcounting, that means that it's still going to be the same size because it's infinite. Natural numbers are the smallest infinity. You can't get any lower infinity than that. And so these are going to be the same size as the naturals. If we can just list this, how can I list this? Well, what you do is you start here, 1, wrap around, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. You can imagine continuing looping that around, counting them up as you go along. Right? 7, 8, 9, 10, 11, 12, 13, 14, 15, and so on. You're just counting all of them up. And that's a bijection. It creates a bijection between the natural numbers and the rational numbers, meaning that even though it seems very, very counterintuitive, because the natural numbers, it's like this, right? Just discrete little bits, and the rational numbers are like this. Right? There's infinitely many between each natural number. Between each natural number, there's a bunch, infinitely many rational numbers. And yet they're the same size. Even though between each natural number, there's infinitely many rationals. They're the same size. That's very counterintuitive. But good news is that this isn't the same for the real numbers, okay? Because the real numbers have a different property than rational numbers. They have infinite non-repeating decimals. Because if you have infinite non-repeating decimals, it doesn't work out, okay? Because if I had a listing, right, where 1 goes to like 0.01, 2, 3, so on, 2 goes to 1. I'm going to just keep 0 out front, 0.1, 5, 6, 7, so on. 3 goes to 0.5611, so on. I don't know. I'm coming up with these on the spot. This is arbitrary. It doesn't matter what you pick. It's completely arbitrary. I'll write out a couple more terms, like right? Just so you get this sort of idea, right? Just choose a bunch of random decimals, right? And you can imagine this is going to be a bijection, right? I say that there's a real number that's not on this list. Let's do a rule where if it's 0, let it become a 1. If it's 1, let it become a 2. If it's a 2, let it become a 3. If it's 3, let it become a 4, so on. And if it's 9, let it become a 0. Okay? What we're going to do is we're going to go along the diagonal. 0, 5, 1, 7, 7, 9. Okay? 0 goes to 1. So I'm going to have 0.1. Then 5 goes to 6. 1 goes to 2. 7 goes to 8. 9 goes to 0. And so on. I claim this is not on the list. Why is it not on the list? Well, if it were on the list, well, it's not the first one because it's different in the first digit. Because it's not 0 there. Okay. Is it the second one? No, because it's different in the second digit. Okay, is it the third one? Well, no, it's different in the third digit. So the fourth one? No, it's different in the fourth digit. And so on and so on. It's different from every single one. It's not on the list. It's an infinite decimal that's not on the list. We just showed that no matter what bijection you think you've made, there's a number that you haven't counted. And there's actually uncountably many that you haven't counted. Okay, because I could do a different rule where 0 went to 2 and 1 went to 1. Or 1 went to 3, 2 went to 4, 3 went to 5, and 9 went to 1, and 8 went to 0, right? That's still going to create different things. And I could create a bunch of different rules just as long every single digit is different from the previous one. You've created a new number that's not on the list, and you have all these rules to play around with that creates different numbers that aren't on the list. And there's just so many more real numbers just by adding the fact that you can have infinite decimals, which is actually going to be countably infinite, meaning it has the same size as the natural numbers. Okay, that's how many decimals are there, because I can obviously count them. But the real numbers of all of those is a different size. And I find that really, really interesting.